Good afternoon, everyone. Welcome to today's AFMS seminar series. It's my pleasure to introduce you today, Professor Christopher Leonardi from the School of Mechanical and Mining Engineering at the University of Queensland. Dr. Leonardi and his PhD in computational mechanics from the University of Wales, Swansea, where he focused on computational modeling of complex fluid particle suspensions. He's a recipient of the Advanced Queensland Industry Research Fellowship, and prior to his tenure at the University of Queensland, he was a postdoctoral research fellow in the Department of Civil and Environmental Engineering at MIT. Chris' research is focused on developing and applying computational models to understand complex fluid-solid interactions such as suspension transport, porous media flows, multiphase flows, and poromechanics. And today, Chris will be sharing his insights into the latest advancements in high-fidelity simulation of complex particle suspensions. Thank you, Chris.
Thank you, Aman, for the introduction, and good afternoon, everyone that's joining along on Zoom. I'm looking at my shared screen, so I can't see all of the participants right now. But thanks for taking the time out to come and listen to this talk. The first thing I would like to say is the work that you see here is the result of a team that includes people such as Lukash, Travis, Nathan, and Lachlan. So I'd like to acknowledge their significant contribution to all of the stuff that I present here this afternoon, some of which will be expanded on in my presentation at the AFMC at the end of the year. So I might see some of you there as well. The first thing I will do before presenting is acknowledge the country on where I'm presenting today. And as a University of Queensland employee, I acknowledge the traditional owners and their custodianship of the lands on which we meet and I'm presenting from. I pay my respects to their ancestors and their descendants who continue cultural and spiritual connections to country, and I recognise their valuable contributions to Australian and global society. The agenda for my talk today looks like this. I will briefly talk through the methodology for the modelling that I present, which is fully resolved lattice-Boltzmann discrete element methods. The detail will be scarce because we don't have time to talk through all of it and then show some applications and results. I'll focus a little bit on the hydrodynamic coupling of the two methods, mention some of the extensions that go beyond just the Navier-Stokes hydrodynamics and hydrodynamic coupling of the two phases, and then show 3 or 4 examples from industry applications where fully resolved simulations have generated really new and interesting insights into the behavior of particles in suspension, and then finish up with some closing remarks. So why do we care about particle suspensions? Well, I would say that particles transported in fluid are omnipresent and their behavior is difficult to interrogate experimentally. So there are a range of applications in science and engineering where suspended particles are critical to a problem. And so just some examples shown here from left to right include sediment transport on riverbeds, cell transport in the bloodstream and also in microfluidic devices, aerosol diffusion and advection in the atmosphere, particularly in enclosed and ventilated environments, hydraulic fracturing, where particles are inserted into the subsurface to simulate reservoirs, which is the basis of most of my research, and then the design of novel fluids such as magnetoroeological suspensions, where electromagnetic effects can be used to control the structure of particles in suspension and therefore change their rheology. And there are many more applications that we can think of varying levels of physical complexity and varying scales as well, I should say. So how do we go about modeling suspensions in our group here at UQ? We use, as I've mentioned, the lattice-Boltzmann method for the fluid mechanics and the discrete element method for the particle mechanics. Many of you will know a bit or a lot about lattice-Boltzmann methods, but for those that don't, It's now a very mature alternative to conventional computational fluid dynamics. And many of the large-scale commercial CFD packages have at least one lattice-Boltzmann solver implemented within them. So it's no longer just a research technique. Lattice-Boltzmann methods are based on a simplified kinetic model, which at the mesoscopic level exhibits is a mesoscopic model which exhibits Navier-Stokes hydrodynamics at the macroscopic level. And some key advantages of the LBM are that we can implement it on a simple, regular orthogonal grid. The mapping of complex structural boundaries is quite straightforward. It can, as you'll see, incorporate a large number of irregular shaped particles in high solid volume fractions. And the nodal operations are usually completely local, which means natural parallelization of the technique and good scaling on multiple CPUs and or GPUs. And so over the last 20 or so years, the technique's seen a wide range of engineering applications in porous media flows, multi-phase flows, aerodynamics, turbulence, particle suspensions, and non-Newtonian fluids. How does this mesoscopic model work? What we do in the lattice-Boltzmann method is we just track the evolution of particle distribution functions, which are a type of probability density function, as they evolve on a regular grid. So if we imagine each particle distribution function as being the probability of some packet of mass at a point in space and time traveling with a certain velocity, then we can evolve each of those packets as they move around on their grid and then how they collide. The lattice-Boltzmann equation, which you can see in here, is therefore very straightforward, which we're just ejecting particles from one node to another, and then applying some kind of collision rule when they interact at a node, which redistributes those particle distribution functions towards some kind of equilibrium. I'll mention boundary conditions here because this is one of the key advantages of the technique. The nature of the method means that boundary conditions are applied at the kinematic level. So that is to say, we know that we are tracking particle distribution functions as they move across the lattice. And so when those functions collide with a boundary, we apply some rule that redirects them based on their trajectory and the orientation of the boundary. And so what we use for static boundaries commonly is what's called bounce back technique, where a distribution function hits a boundary, its direction is reversed, and it then goes on propagating in the reversed direction in subsequent time steps. So this gives us a very straightforward way of mapping complex boundaries to our fluid domain. We don't need to generate a conformal mesh. We can just overlay our boundary, as you can see in the schematic there, and apply our bounce back condition to get what would be some approximation of the no-slip hydrodynamic boundary. The particle modeling is done using the discrete element method, and here I've got an example from my previous life as an engineering consultant where I was using DEM for bulk materials handling. This is a transfer chute at a coal export facility where we see a few 100,000 particles moving through some transfer legs to go from one conveyor belt to another. So DEM has about 50 years of research and academic history. And what we do in the discrete element method is we represent mass using discrete rigid elements which undergo kinematic movement and penalty-based contact. It can be expanded to be coupled with finite element methods and CFD, to use deformable particles, and to simulate continuum to discrete fracture and damage. And so discrete elements origins are in the modeling of say consolidated materials which can fragment and fracture, such as sandstones or other soils and rocks, but also be used to track the movement of bulk materials which are not connected or have some weak adhesive forces. So it's been applied in a range of areas, and just like the LBM, there are commercial DEM solvers that are used widely now in industry. I won't go into the details beyond saying that the key algorithmic ingredients of the discrete element method are how you represent shape, knowing that you can never represent every particle in a bulk system, how you search for particle contact and how you resolve particle contact, how you do your time integration, and then how you parallelize your modeling. Ultimately, with DEM, what we're doing is we're solving Newton's second law for the motion of these particles, which interact with their boundaries and interact with one another via typically a soft contact penalty model. And we can apply other forces as well, such as electrostatics and hydrodynamics, either by some drag law, if you're doing unresolved simulations, or via some immersed boundary type approach if you're doing resolved simulations. So to talk more a little bit about the hydrodynamic coupling, I want to contrast what I'm presenting today with some of the other work that you will see in the literature. So we're dealing with resolved simulations of the hydrodynamics, as shown in the schematic on the right, meaning that the particles are larger than your average cell size in your fluid dynamics solver. Unresolved simulations, as you can see on the left, will have a number of particles that can fit within a cell, and so you modify your CFD result by changing the fluid fraction within a cell and applying some closure models to couple the momentum exchange between particles and fluid. Now here, doing resolved simulations, as you can see in this schematic, implies significant computational overhead, which puts limits on tractable length and timescales and the physics that can be captured. So whilst we will capture a lot of physical detail in this approach, we are constrained by the scale at which we can simulate problems with this approach. Here, for coupling the LBM, we use something called the partially saturated method, which was first proposed by Noble and Torzinski as a type of immersed boundary condition without an additional mesh that outlines the particle boundary. So in this partially saturated method, we actually have our particles mapped on top of our fluid domain, as you can see in this kind of schematic here. And as the particles move over the lattice, they are mapped to the nodes that they're covering. And we then calculate the momentum exchange required to get complete correspondence between the fluid velocity and the overlaying particle velocity, including its translation and its rotation. So typically, to couple a particle to a grid, we need to know all of the nodes, the LBM nodes that are inside a particle's boundary, as well as the nodes that exist at or near the boundary, to be able to calculate what fraction of those nodes are covered by a particle as it moves around the grid. How does it look in terms of modifying the Lattice-Boltzmann equation? It's fairly straightforward in the sense that we just add an additional collision term, which helps relax the velocities of the fluid to the same velocity of the particle at that particular fluid node location. So there's a momentum exchange required to do that, and we sum up all of those momentum components at each fluid node that are mapped to a particle, and we ensure that the complement of that total momentum is transferred to our particles, so that we end up being able to sum the drag force and the torque that exists on the particle due to its interaction with fluid. One thing that's important to note when talking about coupling of the LBM and DEM is that they're both explicit schemes with different time steps. So the discrete element time step is based on a type of CFL criterion, which basically says that the time step has to be small enough to capture wave propagation based on the mass and stiffness of the particles and how they contact. And the Lattice-Boltzmann time step is some function of the grid spacing, the fluid viscosity, and also what's called the relaxation parameter, which is what governs how our collision works in our LBM scheme. So we have two different explicit time steps. And so the simplest thing to do is to force these time steps to be equivalent, but that can put unnecessary constraint on our time integration. when those time steps are quite different. So it is possible to use subcycling, for example, running a number of discrete element time steps within one lattice Boltzmann time step. But that has some practical limits on it as well, because we would be working with, I guess, a static fluid field whilst we update those particle positions. Right, some extensions to the modeling. So far, we've talked about the fluid, the particle, and how they're coupled. How do we add extra physics? The first thing I want to mention, I have more slides related to lubrication in the supplementary material for this presentation, if anyone's interested. The first thing I want to mention is lubrication, because it is a question that I receive often when presenting this work and also submitting work for publication, because generally we don't include an explicit lubrication model in our particle simulations. And there's a very good reason for this. And that is because we can show that at the Stokes numbers that we're typically simulating, the lubrication force becomes a kind of second order type behavior. Noting that for very small particles, the surface roughness becomes, I guess you'd say, not of the same scale, but approaching a similar scale to the size of the particle, or say, let's say an order of magnitude smaller, meaning that the lubrication force as two particles approach one another, rather than approach some singularity, actually plateaus at some finite value, because we have two rough particles contacting one another when we don't have smooth surfaces with an ever decreasing gap between them. And so we've been able to show that with an appropriate hydrodynamic coupling approach and particles of physically representative roughness, that we can actually capture the right hydrodynamic repulsion as particles get closer and closer to one another. We can apply electromagnetic forces to our particles by the implementation of things like the Lorentz equation and Coulomb's law as an additional force field that is applied to each discrete element particle, in addition to their mechanical interactions and their hydrodynamic coupling, and then modify or use those equations to actually control particle behavior. So this is an example from a paper that one of my PhD students wrote, where electromagnetic forces are used to excite particles that are being transported in the channel, and then the vibrations of those particle excitations measured to try and detect where they might exist in, for example, a location underground. We can apply electrostatics, so via commonly known DLVO forces, where we can choose appropriate Haymaker constants, etc., for governing the electrostatic interactions between particles in themselves and particles on the boundaries within which they are contained. And these become quite significant as our particles get on the order of 1 micron or smaller. Above probably 5 to 10, these forces become less and less significant. We can incorporate temperature effects by solving an additional lattice Boltzmann field for the scalar temperature of the fluid, where the relaxation parameter becomes analogous, used to define the thermal diffusivity of our fluid system, and particles can transfer heat between themselves and also between themselves and the fluid. We can extend the fluid behavior to non-Newtonian behavior by modifying our viscosity using the characteristic rate of strain, which is calculated from our rate of strain tensor. And it's a convenient fact in the LBM that we don't need to use finite differences to calculate these velocity gradients. We can actually, from our non-equilibrium functions in our lattice Boltzmann method, so basically information that exists at each lattice node at each time step, we can calculate the stress tensor, calculate the characteristic rate of strain, and then apply a model such as the power law here to calculate what the appropriate relaxation parameter would be for that viscosity, and then simulate, for example, a shear thinning or shear thickening fluid. And we've also published work where we simulate viscoplastic fluids as well, so those that have a yield stress like a Bingham fluid or a Herschel-Bulkley or even a Kwong-Lo fluid as well. And using a similar approach, we can do LES of turbulent flow by calculating the turbulent viscosity and using something like the Smagorinsky model, and then adjusting the local relaxation parameter to solve for suspension problems where the Reynolds number could be up to, for example, in this video that you saw here, 1 million, where large rocks were being vacuumed from the sea floor. And the last thing I'll mention before diving into some examples is the distributed computing. And so this is only really a very brief thing to mention, but because we have two different solvers being run at the same time, and one typically is much more intensive than the other, that is to say that the LVM compute requirement is much more significant than the DEM one. We typically deploy the LVM computations on distributed GPUs and use the host CPUs to calculate the discrete element parts of the simulation. In terms of communication of information between GPUs, the LVM is quite helpful in the sense that the layer of information that needs to be communicated between GPUs is quite thin. It's like one layer of nodes. But with the discrete element method, that layer is quite thicker because we have, from the contact search algorithm, a number of potential particles that a particle could be interacting with. And so we have more information, relatively speaking, that needs to be shifted across between CPUs. What we've been able to show is that as we increase the number of particles, we can get reasonably consistent performance in terms of cost per iteration or millions of lattice updates per second for different hardware types. What we also see is that we get better performance currently with NVIDIA hardware as opposed to AMD. Right, so the second half of my presentation will focus on some applications of LBMD modeling, or DNS, of suspensions, and they will be focused around problems that look like this, where we have a fracture in the subsurface which has some branching cleats or smaller fractures that come off it, and there is a fluid injected into it which is carrying some particles. The objectives of these particles in the context of hydraulic fracturing, for example, in a coal seam, are to place a pack within the fracture that retains high permeability after the fluid injection process is finished. So we do this to maximize the recovery of gas or oil from an unconventional gas or oil reservoir. And so some questions that we would like to know the answers to in this context include: how does a wide size distribution of particles self-organize? Because many of these particles, or propens as they're called, come in distributions that are quite poorly controlled because it's quite expensive to do very specific size or sizing of a particle that is injected. What are the things that drive clogging and screen out? What is the carrying capacity of a fracture at a given pressure? What's the permeability of the fracture after it closes and the proppant embeds into the coal or the rock that's been injected into? What's the optimal carrier fluid rheology? How do particles leak off into cleats and smaller fractures? Or how do microparticles or low quality particles help stimulate a reservoir? And so I've got a number of examples which touch on some of those questions. The first one relates to transverse migration in a channel. So some of you will know that when you inject particles or flow particles through a confined geometry, such as a channel, they will organize themselves due to the competing processes of inertial migration and shear-induced migration. And so what we did here a few years ago with Nathan's PhD and Lukash's assistance was look at this numerically using this test cell that you can see here in the bottom left of the image. We have periodic geometry between two walls where a suspension of microparticles is flowed in one direction in that channel. And we observe the way that those particles migrate over time. What we can see in the middle here is some different size distributions for the particles. You can see kind of the scale that we were dealing with here. So radii on the order of 1 to 4 microns and its diameters of 2 to 8. And we describe these particle distributions by their first 3 statistical moments. So mean, standard deviation, and skewness. So we've got here 3 different particle distributions, and then P21 and P22, which have the same mean as P2, but have the different standard deviation and skewness. Before we start asking questions with this model, what we did was some validation where we compared the results of the simulator to some experimental work, some density functional predictions, and some other LBM work, and found that with appropriately tuned friction coefficients, we can replicate the data that exists in the literature quite well. So that's obviously very reassuring before we start trying to determine anything new with this modeling approach. One of the first things that we showed is that the migration of particles is dependent on their degree of polydispersity, and we can characterize that polydispersity by those first 3 moments that I mentioned. What we've got here in the bottom 2 graphs here is a plot of this scalar dispersion, this scalar dispersion function C. Basically, what C tells us is how close or far a particle is from the center plane of the channel. So if C was 0, that would mean that all particles existed on the center plane of the channel. If C was 0.5, all particles would exist on the walls on either side of the channel. So as C gets smaller, we have particle migration towards the midplane. And so in these graphs, we can see that from the initial configuration, we run these over times as measured by the length divided by the width of the channel, and we reach some equilibrium position for our different distributions. And so we see that for the different degrees of polydispersity, we have different degrees of migration towards the center of the channel. What we were also able to show is that for polydispersed suspensions, the characteristic behavior is much the same as bidispersed suspensions. So just as the rheology of a bidispersed suspension is analogous to that for a polydispersed suspension, we also found that the migration behavior for a polydispersed suspension is similar to that for a bidispersed suspension that has the same statistical properties of its distribution. The most interesting thing to come out of this work, though, was the emergence under certain conditions of this plug of preferential small particles that forms at the center of the channel. So to provide some context for this finding, if you are injecting small particles amongst your proper suspension into a hydraulic fracture, you might like the smallest particles to leak off into branching pleats and fractures to provide some stimulation there. What we found is that when the local solid volume fraction got to around 40% or higher, the smallest particles in the suspension would actually migrate towards the center of the channel. So they would end up in exactly the opposite location to where you would like them for this particular industrial application. The theory that we proposed in this publication from a couple of years ago is that those smaller particles are able to make their way to the center of the channel because of their high shear rate fluctuations, and so their ability to basically wiggle their way from wherever they are into this equilibrium position in the center of the channel. And so this was a really interesting finding for us. Moving on, the next application I wanted to talk about relates to particle clogging and screen out, where we are interested in what solid volume fraction is required for particles to start forming a clog, which is a small arch or bridge of a small number of particles, and then later on jamming or screen out, where a large number of particles either completely come to rest or almost completely come to rest. And so what we did to investigate this was design a synthetic numerical test cell, which had some arbitrary synthetic roughness on the side, because what we found is that with perfectly smooth walls, we couldn't initiate any clogging whatsoever. And then in this channel, we flowed particles at different solid volume fractions for different widths as measured by the ratio of the width and the particle diameter. And so for varying solid volume fraction that you can see on the x-axis of these graphs, we're able to determine the probability, which is on the y-axis, of a clog forming. And so what we see here is the data that come from simulations. And I've got two graphs here, which shows how the distribution of results changes as we run more repeats of the same test. So on the left, we've got 20 repeats of the same test at each solid volume fraction, and on the right, we've got 40. And obviously, when we do 40, the standard deviation of our predictions gets narrower. We see that there. So we've got an increasing probability of clogging occurring as our solid volume fraction increases to, in this example here, about 10% or above. And the two key numbers that we pull off these graphs are what we call 5-5. So the 5% confidence interval for clogging to occurring, that should say 5, not 95. And phi 95, which is the 95% confidence interval for clogging to occur. So those two numbers kind of encapsulate the region in which the probability of clogging is changing significantly. So if we look then at the plots for phi 5, that's this line here with squares, and phi 95, this line here with circles, we get this region here hashed in blue, which shows the change from low probability of clogging to high probability of clogging. The white area below, there was no clogging detected and no chance of clogging occurring. And the gray would be the region where there is always clogging occurring. And so the first interesting result that you see here is that the relationship between solid volume fraction and the width of the channel is non-monotonic. So that is to say that as we go from somewhere like 1.2, so the fracture is only 1.2 times the diameter of the particle, the solid volume fraction required to clog actually goes down as we get to this critical number around 1.8, and then thereafter it increases as we get wider and wider. Now, the reason for this behavior is that when the fracture is very narrow, the particles transport in a monolayer, and there's no potential for them to form two particle bridges. As we get to 1.8, the possibility of a two-particle bridge forming in the fracture, it becomes quite high, or relatively high, and so we get this drop in the solid volume fraction required for clogging to occur. But then as we get wider again and we go beyond 2 particle diameter widths, we see that the solid volume fraction required for clogging increases quite quickly. And we in fact also see this region between 2.1 and 2.3, where we're about 2.3, where we weren't actually able to measure any clogging whatsoever. We could also show the influence of the friction coefficient, so the roughness of your fracture or your particles, and how that decreases the solid volume fraction required for clogging to occur. And that's what we see. That's kind of an intuitive result, but we see that mapped out quite clearly in this graph here on the right. What we could then also show was, because these are quite small particles, so on the order of 1 to 10 microns, we could show the influence of electrostatic interactions on clogging behavior. The key takeaway from this slide here is that the adhesion due to electrostatic interaction between the particles in the walls quite substantially reduced the solid volume fraction required for clogging to occur. So if we look at the dark markers on this graph here, we see that as this non-dimensional number, the wall adhesion increases, the solid volume fraction required for clogging to occur decreases quite quickly. And we see that over here in the graph on the right-hand side, where we plot our phi5 and phi95 against the wall adhesion number, which is defined over here. And we see that the solid volume fraction quickly drops down to a very small number required for clogging to occur. So in an industrial sense, if the electrochemical properties of the fluid particles and the medium that they're flowing in are such that we end up with substantial attractive forces between our walls and our particles, we will see that borne out in the aggregation of particles on the walls and an increased likelihood of clogging as particles flow. Right. Moving beyond that synthetic analysis of clogging, we've done some work more recently where we have studied the transport of non-spherical particles or angular particles in more realistic fractures. And so the motivator for this work was an industry partner was curious about the implications for using what is called a non-API or a non-standard sand as their injected proppant. That stuff looks like this photo here in the bottom left, and it has quite different properties in terms of shape and size distribution to more industry standard products. So if we look at this non-API product, it has roundness and sphericity, which are quite fair bit lower than an industry standard product from the US called Wisconsin sand, which has roundness and sphericity of 0.9. Size distribution is also a little bit different as well, where this is in mesh and not in micron. But yeah, sort of on the order of 0.3 to 0.5 millimeter in diameter. So the question is, how does a poor quality or non-standard product behave when flowing through a fracture? To answer this, the first thing that we do is come up with a way for defining how our fractures look. And so a few years ago, Lukash found a mathematical model in the literature based on a roughness power spectrum that allows us to generate fractures of different tortuosity, different local roughness, and different surface correlation and separation based on just three parameters. And so with this model, we're able to generate lots and lots of different realizations of fractures that look like this image on the right-hand side. And this example here has an opening of 0.5 millimeter, a mean surface roughness of 20 micron, and perfect correlation between the two surfaces. Obviously, in geoscientific flows, that surface correlation is probably never 1. It's something less than that, but I don't go into that in too much detail here in the results that I show. The next thing is to address is how to represent these angular particles. And so Lachlan did some work last year and this year in actually generating faceted convex particles that capture the shape and size distribution of this non-API sand. And so that's what it looks like here on the left-hand side. But from the perspective of simulating these particles in transport over hundreds of thousands of time steps is a bit of a problem, computationally very expensive. And so our approach to dealing with this is to represent particle angularity using clumps of spheres that we can see here on the right-hand side. And those clumps can be constructed as either 1D shapes, so in a line, 2D shapes, here you can see like a triangle, 3D shapes that you can see in this tetrahedron here. So we've got results for different ratios of A and R, where A is the spacing of the length between the centers of particles, and R is the radius of the particle. So what do they look like? So from left top, we've got spheres. to our linear clumps, bottom left, our 2D clumps, and then bottom right, our 3D clumps. And so you see the way that they interact. I should say that these particles are designed to all have the same volume, which is why the spheres look different, look of different size in each one. So we needed to keep something constant, and so the decision was made to keep the volume of each particle the same. And so when we talk about d, lowercase d for these particles, that is the diameter of the sphere of equivalent volume. So then we look at the results for these analyses, and each dot here represents a unique simulation. So there's quite a bit of computational data generated to make each of these graphs. And in this first slide here, we've got our one-dimensional clumps at increasing fracture width. So these are all linear clumps at width on W1D of 2.1, 2.5, and 3. So the fracture is getting wider as we go from left to right. And what we're plotting is the flux of this suspension compared to that you would get from the cubic law for permeability. So basically H cubed by 12. And we plot this at different solid volume fractions, so getting up towards the theoretical packing limit of particles in the flowing geometry. So what we see here, the solid dark lines are the results that we get from our simulations. So here, the circles are just a sphere, because A on R is 0. Then the triangles are A on R is 1, so getting a bit longer, and then A on R is 2, getting a little bit longer again. For comparison, we've got some empirical and analytical models, which you would find in literature and are commonly used in industry to describe these types of behaviors. So we've got our suspension viscosity based on a Marin-Pierce correction that you can see here. And we've got the screen out criterion that you would get from this paper by Smith and Schreiber-Pilersky, which basically decides or defines the point at which particles will no longer flow. So the first thing we see is that we don't get a sudden drop in permeability at any certain solid volume fraction. The relationship between permeability and phi is continuous in all cases, even when the fracture is narrow, but it deviates most from the empirical models when the fracture is narrower. So as we move from left to right, we see that two things. We get closer to this Krieger-Doherty law. We also see less influence on the aspect ratio of the particle, which is why all these curves are falling one on top of each other. The third thing I guess we would say we see is that at high solid volume fraction, we don't get very good representation of the behavior via this Krieger-Doherty suspension viscosity model. It maps much more closely to a Kozny-Kármán type response for flow through a packed bed. If we go to our two-dimensional clumps, we see similar kind of results, although at our narrowest fracture, the ordering of the behavior is a little bit different. This is aspect or A on R of equal to 1. And then on A on R equal to 2, the permeability or the flux is actually improved. And our thinking there is that as the particles, these are triangular particles now, and as they get a little bit bigger, they align themselves preferentially with the flow direction and actually transport a little bit better. Then when we go to our 3D clumps, we actually see in our narrow fractures that particle angularity here is having the biggest influence and reducing the flux that we see in the narrow fracture quite substantially. If we then compare how these particles look in the narrowest fracture, so that's W1D or equal to 2.1, we can see the difference that 1D, 2D, and 3D clumps have on the behavior. And so we can see here the difference between, say, a 3D clump at 20% volume fraction is quite different to that for a 1D clump at 20% volume fraction. So we're talking about 40% reduction versus a reduction to 20% as well. So the last thing I will talk about just quickly before finishing up is then if we created a pack in a fracture out of these angular particles, how would smaller particles percolate through them? This is a common problem in the industry where fines that are generated from the reservoir flow through the porous pack towards the wellbore and damage pumping equipment that exists downhole. And so what Lachlan did during his project was create some packs of the different particles. So here's our non-API sand, and here's the two other industry standards, Wisconsin and the other one. Just spheres, sorry, I should say. And then flowed 100 mesh suspension through this bed to see how they percolated. And the results were quite interesting. What it showed is that the non-API sand was able to admit a significantly greater proportion of the transported particles into the pack. And that's shown by the yellow stars or orange stars here, showing the percent of total deposited particles as we get deeper and deeper into the pack. What this means is that the non-API pack is able to admit a lot more particles and have a lot more flow through it completely, but it would also exclude particles within the pack as well because of the wide variation in the pore throat size. And so when we look at the effect that that would have on pressure drop in the packs, what we saw is that for the non-API sand, which is denoted in labor here, we see quite significantly increased pressure drop in the pack due to the deposition of fines particles that are flowing through it. And so we have a potential problem here later in the life of a fracture and a well where the pressure loss increases and reduces the rate at which water and gas flow towards a well. So with that, I think I'll just quickly skip over this last application, which is talking about the influence of non-Newtonian rheology on particle leak-off completes, and finish up with some closing remarks. We've gone a little bit longer than I'd hoped to talk about the outlook and future work. So we've got a modeling methodology that is applicable to a range of science and engineering problems. So certainly not just hydraulic fracturing, but in filtration, in biological flows, and a range of other things. In the area that we're working, there's still a lot to study in terms of the influence of geometry, fluid rheology, and operating conditions, and potentially supplementing our analysis with fracture imaging, like you can see here in the bottom left, where we've done some digital optical microscopy to try and inform the model of fracture geometry and generate fracture realizations which have some physical basis. And then, of course, upscaling these data to industry relevant length and timescales, like you can see here, where some preliminary work that Lukash has done can potentially take the information that we get from our small scale simulations and apply that in a large scale model to predict fracture, particle deposition, and transport in much larger fractures, where here in this example, we have a suspension entering from the top left corner and leaving from the top right. Color contour is showing the solid volume fracture, and you can see here the growth of a bed in this fracture slot with time as particles settle out and are obstructed by the geometry. So that's all I have. Yes, I've talked a little bit longer than I'd planned. For anyone that's interested to learn more about the tools that we use for this analysis, it's all open source. So the LBM is done using TCLB, a code that Lukash created a few years ago, and the DEM is done with lights, which is has been around for a while as well. So if people want to know more about the code, download it, play with it, and find information about it on the website. And with that, I'll finish up and take any questions.
Thank you, Chris, for this interesting and insightful talk on particle suspensions. So we would like now to invite the audience. If you have any questions, please feel free to unmute or type in the chat box your questions. Yeah.
Hey, Aman. Hi, Richard Samrock here. Hi, Chris. Great talk. Really impressive animations too. I think I had two questions, maybe more on the underlying algorithmic stuff. So you mentioned you're seeing better performance on the NVIDIA GPUs than you see on the AMD. Do you know why exactly that happens, and do you know how to fix that, or is that not fixable?
So some of it is currently not fixable. I think as Lukash would explain it to me, the issue arises with the way that data are warped on the AMD cards. And so our data structures are not optimally aligned for distribution in warps on the AMD card. So we've spent quite a bit of time working with a company in the US as part of the Pawsey Pacer program to improve performance, and the graph I showed is the outcome of that. So that's kind of the best we were able to achieve at this point in time with that particular AMD card. That's an MI250.
Okay.
So we're kind of stuck at the moment, I would say, in a situation where it's takes about twice as long to solve a problem on an AMD card versus an NVIDIA card.
Okay. Was that with fluid numerics, or?
Yeah, that's right. Yeah.
Yeah. And then the other question I had, I mean, your application focuses a lot on, suspensions, underground, etc. But I was actually curious, is there any way to extend this to compressible flows? So I'm kind of thinking, high speed particle deposition or something like that.
Yes. Yeah, absolutely. So that's not a particular focus of what we're doing, but for sure, yes, absolutely. I think some people have tried and do this with unresolved compressible flows, but as I said, the stuff we do here is resolve simulations, because we're really interested in the physical behavior that emerges when you correctly capture the hydrodynamics and the mechanical interactions.
Yeah, I was just wondering, because the LBM method, how well does it kind of extrapolate to compressible flows, right?
So standard LBM not so well, but there are other kind of like extensions that can do compressible stuff.
Okay. Yeah, great. Thanks, Chris.
No worries.
Perhaps I can ask one question until some people gather their thoughts. So in slide number 28 or 27, where you talk about the segregation of the particles between two plates. So the reason for this, you said, was, again, you showed it with a shear rate.
Yep. I'll just reshare.
Yeah. So my question is now, the plates are the bounding plates or the boundaries. Are they? I mean, the fluid pressure, is it confined, or the fluid pressure can dissipate through those walls?
Oh, no. So that it's confined. So we just use the small sphere pack there to provide some surface texture for the I guess the wall roughness, right? So that fluid boundary is not porous; it is impermeable.
Okay, so if the fluid pressure is confined, so there is this work by the group by Elizabeth Guaselli, where they look at the suspension of this dense suspensions, where they show the influence of the total pressure, especially coming from the fluid.
Yes.
Does that account somewhere in your expression? Because here I see it's mainly the contact dynamics, right? From this equation, the T is a particle kinetic energy.
Yes, yes, that's right. So this is just the root mean square shear rate of the fluctuations for these particular particles, right? So it's basically the ratio of their energy and their size, which gives a measure of their shear rate.
Okay, my question was like, where does the fluid pressure go into here into describe, because there in the work by Elizabeth and their group, they show that they call this number the viscous number, which is the ratio of the confining pressure and the shear rate. Is the important parameter which defines the segregation. So I was curious to know whether this also applies here, but perhaps this is mainly contact dominated configuration.
Well, I'm trying to think. So here we drive the flow with an acceleration in one direction. So there is a pressure gradient that emerges in the transverse direction due to the particle pressures and their interaction with the walls. And so the pressure field in the fluid will ultimately have some influence on the kinematics of the particles themselves, right? So and that's reflected in their movement, their fluctuations, and their kinetic energy.
Okay. Yeah, thank you. Another comment, perhaps, if I can ask another question.
Yeah, absolutely.
Yeah. Where you talk about the lubrication modeling. In the context of in my work where we look at sediment transport, also we observe similar where the lubrication is less important, and we usually don't incorporate any lubrication model. But usually we end up defending ourselves to the reviewing process.
Yes.
Many people say this lubrication force is important. So I find it interesting that you were able to show that the lubrication force is less important when you have done systems.
Yeah. So if you look at so for the Wright-Stokes numbers, you can show quite clearly. And if you look at the paper on the clogging, it's the reference will be at the end. In JFM, we've actually had, through the review process, we had to run a whole bunch of simulations that showed. So it's this paper here that showed that the addition of lubrication forces is not necessary. And we avoid it because it's a bit painful, right? You either add it explicitly as an explicit force, which is prone to instability because it can become singular, or you apply it implicitly, which becomes a bit of a pain numerically, right? So we've done, and I've got some results here somewhere. We've done explicit implementation of lubrication forces before. Where is it? Here. Where we can show, you know, when you change your cutoff distances, how the force changes as two particles approach at different velocities. But ultimately, when we're dealing with particles on the order of, so like 5 to 10 micron, and their surface roughness is on the order of 1 micron, you don't have, you know, perfectly smooth surfaces approaching one another. And we don't, and for that reason, you don't see that spike in pressure and repulsive force as they approach contact. And there was actually, I think at the last AFMC in Sydney, there was a really nice experimental paper presented by a gentleman from New Zealand where he'd done some pendulum tests of spheres in suspension contacting one another and showed kind of similar behavior.
Thank you.
Excuse me, can I ask you a question?
Hi, Mohammed, I can hear you, but
Yes,
you're
please.
very.
Yes, thank you. So my question is about, thank you, Chris, first of all, for your nice presentation. It's very informative. So back to the slide, I think, number 28, again, about the segregation.
Mm-hmm.
Yeah, I just wondering, is this the shear, the type of shear that's affecting the particles, the small particles to be more in the center and the large particles close to the wall? Because I'm not quite sure, but I have some papers that having the uniform shear flow, shear field, and the small particles become more close to the wall and the large particles at the center. So I just want to know, is this the is this type of pressure-driven flow that pushes the small particles to the center?
Oh, so we're not able to say make it such a simple conclusion. The competition between inertial migration and shear-induced migration depends on a number of factors. So it will depend on the solid volume fraction. It will depend on the shear rate of the overarching flow. And as we see now in these new results, it will also depend on the ratio of the sizes of the particles. And so if you read the full article, you see there's, I guess a more full description of the cases where inertial migration dominates over shear-induced migration and vice versa. So we can't say, in this particular case, in this particular geometry, does shear-induced migration dominate over the other? It very much depends.
Yeah. Okay. Thank you.
Okay, I have just one question. Can I ask?
Yes.
Yes, please.
Yes, Chris, thank you for your presentation. I have just one question. Can you extend this model for porous media, and if you apply it, how it works? Is good or?
So you mean for particle transport in porous media?
Yes.
Yeah, so that's basically what the last example was that I showed. If I just scroll, whoops. Yeah. So what we did was we created a porous pack. So that's the rendered, the blender renders of the 3 different packs there. And we use those packs as static boundaries. So they form effectively a porous medium. Whoops, I don't know why that's changed. My mouse has started playing up. Yes, we use those packs as the boundaries. And then we started flowing smaller particles, so kind of like order of magnitude size smaller particles through those packs, and monitored where they screen out or where they segregate mechanically and where they don't, where they flow through the entire pack. And then we were able to measure things like you see in this graph, like the deposition depth in the different packs and the pressure drop across those packs as a result of the particle deposition. So yes, yes, it can be used for porous media, and I would say yes, we're already doing it.
And for generating the equation for LBM, so you need to change the LBM equation for porous media, or just you add the
No, it's just so
force term.
so for this the interaction between the LBM and the static pack here, we just use the bounce back boundary condition, and that's it.
Okay, so you don't change the LBM equation for the porous part.
No.
Okay, great, thank you.
No worries.
Maybe I can ask one final question is in terms of implementing the parallelization. So if I understood correctly, you have 2 independent solvers, right? For the particle and for the fluid.
Yes.
Are they running concurrently? And how do you manage now with the
so the LBM computations are deployed on the GPU, and the DEM is run on the CPU of the node that's holding the GPUs.
Okay.
Right. So they're running on separate processes, and then they need to run somewhat synchronously between time steps. So we try to do our best to shield the communication. So the DEM requires more communication, a slower communication than the LBM. So we try to do that communication whilst the LBM is finishing its computations, because there is more workload associated with the LBM compute. And so we try to shield the DEM communication as much as possible by doing that whilst the LBM compute is finishing.
Yeah, that's interesting. Yeah, it must be a lot of API implementation going on.
Yeah. Lukash has done a lot of work on optimizing the efficiency of the coupling.
Yeah. Thank you. If there's any further questions, thank you, Chris, for this interesting talk and finding the time to share your work with us. We appreciate it. And yeah, if there's any further question, we will stop the the session is now.
Thanks, Aman. Thanks, everyone.
Thanks, Chris. See you then in AFMS.
Bye.
Bye.